This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 46. We continue our discussion with the founders of the tools now in the Ansys world with an interview of the two founders of CFX, Paul Galpin and Brad Hutchinson. Greetings from Vail, Colorado. This is Eric Miller, one of the owners of PADT and your host here on today's podcast. I am in Vail, Colorado, as I said. And yes, it's beautiful, especially the temperature. It's been 110. It's been over 110 Fahrenheit in Phoenix for a little bit longer than normal this summer. So it's been very nice to have the cool weather and the beautiful mountains. I'm here for the Rocky Mountain Life Sciences Investing and Partnership Conference. It was a great day of listening and talking to startups from the region who are making healthcare better. Some very amazing things, lots in the area of genetics and drug delivery and digital medicine, really cool stuff. Unfortunately, this time there was nobody talking about simulation, so I'll stop there because this is All Things Ansys. Also, I will note that this episode is an interview again with some founders of one of the tools in the Ansys suite. And because it was such a great discussion, it went a little bit long. So we're going to cut the beginning and end of the podcast a little short and focus on the interview. I'll also do one more apology, which is that I didn't bring my fancy headphones with me on this trip. I'm using my music headphones, my Bluetooth headphones. So it's a little sketchy, but hopefully you can understand me and it won't be too bad. And I won't talk that much anyway, because we're going to focus on the interview. Which brings us to the topic of today's episode, and it was an interview with two founders of CFX. For those who don't know, CFX is a general purpose computational fluid dynamics code, CFD, and it was acquired by Ansys Inc. a bit back. A fun fact, Ansys has acquired 4 CFD solvers that I know about. Back in the early days of the code, they acquired Flowtran, which is a Fortran-based FEA CFD solver, and it was actually integrated into the Ansys solver, what's now Ansys Mechanical APDL. Most people don't know that. There was also an acquisition of a company, I think that was out of Palo Alto, California, that had a multi-physics tool. I can't remember the name, but it had a CFD solver in it as well. Nothing really ever came of that. Then we really got serious when Ansys acquired CFX, which is a fantastic tool, and then Fluent. But we're here to talk about CFX today, a tool that's near and dear to PADT's heart because of its strength in turbomachinery. As many of you may or may not know, most of us at PADT, over half, come from the turbomachinery world, and we love CFX. We love what it can do in the turbo world as well as outside the turbo world. It is really a fantastic tool to use. We really like it. And that's why we virtually sat down with Paul and Brad back in July. I do apologize. I said that was my last apology. There'll be more. I apologize to them and all of you for taking so long to publish this. We do schedule these podcasts usually around webinars and other events. So we talk about what we're going to talk about at the webinar or event. And so we didn't really have an empty spot till now to put this one in there. So I'm happy to say it is time. And I think you will enjoy hearing what they have to say. I'll let Paul and Brad explain the rest and introduce themselves and give you their background. And please do enjoy.
So welcome with my discussion today with two people I've had the pleasure of knowing for quite some time, and Paul Galpin and Brad Hutchinson, who are two of the founders of a piece of software and a company called CFX, which is part of Ansys Inc. now. And they were kind enough to join me from the Great White North, which is neither white but still great, I guess, right now, and discuss kind of how they got where they are. So, hi, guys.
Hi, Eric.
Hey, Eric.
Good. So why don't you introduce yourselves and give us some background on kind of up to how you ended up doing numerical simulation. A lot of people don't, in high school, you don't go, I really want to do a career in numerical simulation. So, how did you end up in that world? What did you major in college and why? And how did you end up in the world of simulation? Why don't you go first?
Brad, Paul.
Go first. Paul, go first. Paul, go first. Okay.
Yeah, so, I think in secondary university, We were in some mechanical class, and they showed this movie. No videos back then; it was an actual movie, and part of it was on gas turbine blades and how the temperatures went up. And then partway through, they showed this thing called FEA and these meshes and these nice colorful plots. And I thought, man, is that ever cool? And kind of from there, early on in undergrad, I ended up taking a FEA class and had a work term one time up at Chalk River, and they were doing CFD up there, and started reading Patankar's book while the laundry was being done and so forth, and kind of got bit by the bug at that point.
Cool. And this was Waterloo that you were at?
Yep, University of Waterloo, yeah.
Okay. How about you, Brad?
Yeah.
Well, as an undergrad, I went to University of Waterloo, and I had classes with this really excellent professor, Professor George Wraithby, and I later came back to do a PhD with him. But between undergrad and PhD, I went to University of Toronto, and I did experimental work, or largely experimental work, but with some numerical parts to it, basically inviscid flow calculations and classical boundary layer calculations. So I did some computer work, and doing experiments is difficult. I have a lot of respect for people who do experimental work. So I think I had enough of it for the time being. So I decided to go into numerical work, and George Wraithby, who I already mentioned, was a top guy in the area of numerical methods. And since I had known him from the past, I went back to Waterloo and did my PhD with him. And so that was really, that got me into numerical simulation.
Cool. And that leads into my next question, which is, CFX is a fantastic general purpose code and commercial code, right? And so, were you guys sitting around in the school cafeteria and said, "Hey, let's write our own code"? Where did the decision to go ahead and write a piece of software that you could sell come from?
Well, I guess a little bit of the background is, both Paul and I worked on development of numerical methods, because in those days it wasn't clear how things should be done in CFD. There were all kinds of different methods, and none had really solidified. And the ones that did exist, they needed augmentation. There were things to be done. It's much different, 40 years ago or whatever it was. Things were much different. The methods weren't nailed down. A lot of work yet had to be done on development of solution methods, discretization methods, even the basic framework and structure. So we got involved in development of methods. And for me in particular, I was working on environmental flows, specifically rivers. And there were a great deal of problems in getting solutions to such flows. Also, of course, in the early 80s, the computing power was, incredibly less advanced than it is today. So we had to develop methods that would yield solutions without having the tremendous computing power that we have today. So we started developing methods, and we sort of got drawn in. Once we started our company, we got drawn into a variety of applications. So perhaps that's what led to a general code, because we got working on environmental flows, on turbo machinery flows, nuclear flows, as Paul mentioned, and a variety of different things. And so the code had to be fairly general in its ability to do a wide range of flows, for instance, incompressible, compressible, supersonic even, with heat transfer, with a variety of different capabilities. And in those days, there wasn't much in the way of general codes, or one or two, but they were quite limited. So we got contracts with a variety of companies, and they all led us in a variety of directions, and that sort of yielded general. Paul, you can probably add a lot more to it than that.
Yeah, well, we didn't know what we didn't know, so that was quite helpful. We weren't constrained by any facts at the time, and we were all excited by our coupled solver work. I was doing coupled solver, and Brad was doing multi-grid type work. And George Ratheby, he'd experienced this several times before, where he got a batch of graduate students, and they would really come up to speed and make a contribution, and then they'd all disappear. And he'd been through this cycle a couple of times, and there's Brad and I and Jeff Vandermaal and Michael Raw as well. We were all finishing about the same time, and George gathered us together and says, don't disappear. Let's start a company. Huh? Let's commercialize this stuff. And that was in 85.
85, okay.
And at that point, most of us didn't have any mortgages or kids or commitments, and so we kind of naively said, we can do this. And so off we went. And those days, the software planning when we started was only a few minutes to head off into writing a piece of software that might last for 10 years. We had to learn software engineering at the same time too. And we took what we learned, and George really was well known worldwide, and he got us some starting contracts.
Great. So he was part of the company initially.
Oh yeah, he was the president, and he knew how to talk to real customers and get sales. And we went out over and started plotting around Europe and various places in the U.S. and Canada as well, and got us those startup contracts. So
cool. So how'd the name CFX come to be?
Brad and I are one company before that.
Yeah.
So the first company was ASC, Advanced Scientific Computing.
Okay.
And that made TaskFlow, which is the first code that Brad and I were involved in. And then the roots of TaskFlow became embedded in CFX.
Okay.
Yeah. So ASC and TaskFlow were a private company until 97. And Brad, was it 97 or 96?
Yeah, 97.
97, yeah. So 97, we got purchased by AEA Technology.
Okay.
And AEA Technology was this government-based company with atomic energy in the UK, and they had the code CFX4. And they were trying to go to unstructured, from structured to unstructured meshing, and so were we. We were going from TaskFlow to TaskFlow for CAD. And they were in chemical industry, and we were in not the chemical industry. So we were actually a reasonable match, and so they purchased us. And that's how it happened. And the name CFX, as far as I understand it, AEA Technology originally had a code developed called Flow3D, and it was in conflict with another code called Flow3D from Los Alamos, I believe.
Yes.
And so they had a bit of a legal tiff over this, and during that time, they didn't know what they were going to call their new code, like CF something. So they put CF asterisk. CF asterisk, whatever that asterisk might be filled in. And then it got a little hard to say, so it turned into CFX. And then it stuck.
It's a great name. I did not know that. That's fantastic.
Yeah. And then when the two groups got together, we really did merge technologies. And then TaskFlow and CFX4 became CFX or CFX5 today. Yeah.
And that's the code we know that's a part of the Ansys family. Is that?
That's right.
Yeah.
Right. And then Ansys bought us in 2006.
Yeah.
2003.
Oh yeah, Fluent was 2006. Sorry.
Yeah. 2003.
Yeah.
Cool.
2003.
So that gives us a kind of a background on how you got where you were, and I really like knowing like where the names came from and who was involved early on. Is there anybody that was part of that early team you want to mention that give a shout out to that we haven't mentioned already? Kind of put you on the spot there.
Probably lots.
Yeah.
Well, I mean, from the ASC side, I mean, George Ratheby, our professor, he was instrumental. Without him, we wouldn't have had TaskFlow CFX or anything else, and he was kind of the key guy initially. And Jeff Vandermaal, he was the same as Paul and I. He had done his PhD, and in particular had worked on solver methods and extending incompressible methods to compressible flows. And then there was Michael Raw, who joined us a little bit later. But Michael was instrumental in sort of the basic, this element-based structure. He had done some of that work on his PhD. So those were the main guys, or we were the main guys, I guess, with ASC, and then we joined up with CFX, and in the AEA technology world, there were some other good developers there who made some great contributions as well.
Mm-hmm. Cool. Did you guys write in Fortran or C back then?
Fortran.
Fortran, good.
It's my first language still. English is second language.
I learned, the reason why I even know the University of Waterloo exists is because I learned Watt 5 in college. Yeah, which is from for those of you who are young, it was a teaching version of Fortran that the University of Waterloo developed that engineering schools used around the country around the world to teach Fortran. So kind of a forgiving version of Fortran.
Yeah, it was very, very forgiving. And maybe that's the other point that we hadn't mentioned is that, it's much different today in terms of computing capabilities, but in our early days, the early 80s, late 70s, early 80s, Waterloo had powerful, for the time, computing capabilities. So this was one attraction, and we had access to these old IBM 4341 and 4381 computers, which were, heavy stuff at the time, and that enabled us to do the work that we did early on. And of course, they had pretty good infrastructure, and as you mentioned, Watt 5, so there was a lot of good support there for anybody doing computer-related work. So that was certainly a key enabler for us in the early days.
Yeah. I remember one of George's early CFD codes. It was on cards, and he had this tremendous, Navier-Stokes CFD code on cards, and he took it down to the Heavy-Duty Computing Center at U of W and started doing his simulations. And they got back to George after a while and says, Rafe, there's something wrong with your software. It's broken. It's running forever. He said, no, it's a CFD calculation. They didn't be taking that long to run.
It's still true today, right? The CFD run never really converges. We just accept that it's converged, right? That is really cool to know. So kind of thinking back on where CFD is today, is there something that surprised you, something that you didn't expect that would happen in the world, and it did happen, or something that you thought would happen and didn't happen?
No, go ahead, Paul. You're still working.
Well, on the one hand, there's tremendous success with CFD as an industry now. The codes are accessible, and the methods are quite. And, someone can really walk up to a piece of software, a commercial CFD software, and they can get an answer. It's still very challenging to get a quality answer. It's surprising to me that the numerical methods have really stagnated. So there's work going on in universities, of course, in higher order methods and so forth. But by and large, there's still the two communities. There's the density-based community, most of the commercial codes are pressure-based. On the pressure-based side, the whole community relies on, reach-out approach to the numerics for collocated mesh. It's really surprising that it hasn't gone past that, really, as far as I know. And certainly not commercially. Maybe it's out there somewhere at a university that hasn't made it to mainstream yet. But it's surprising how little change is happening today in numerics. You go to a conference like IGTI and you just don't see very little on numerics now.
That's a good point. People are adding things, equations to the numerics. So they're pre and post processing, of course, is a huge focus, especially meshing, or they're working on the efficiency of the numerics. But you're right. The numerics themselves, I never thought about that, have not really changed. Yeah.
And you go to a conference like GTI, and it's really a testament to the state of CFD. Almost everyone there that has CFD in their presentation, they're doing a design, and they're talking about their design, and they're talking about the improvement of their, some aspect of their machine. So, by the way, we use CFD, we use CFX, and we did this, that, and the other to it. But it's just kind of mentioned in passing that, of course, we're using CFD, and of course it works. Is what a lot of the talks are. Now, the truth is it's still a lot of challenges out there for CFD.
Yeah.
And the challenges are very similar to they were a long time ago. It's still a long, painful process to make meshes in a lot of cases. It's still, you really have to be careful to do a quality calculation. To get a calculation, it's hard to get a quality calculation.
That is very, very true, and we see that every day here at PADT. I got an answer, but we were actually doing a relatively, what we thought was a relatively simple mixing problem for a water treatment plant, and it just was not working. It was not working, and it was one of those things where one little change in a parameter, oh, boom, there it is. Now it's converging, and everybody's happy. So it still can be a pretty finicky behavior. Yeah. So, that kind of begs a question of, do you think we'll see any new CFD codes? I mean, I don't know what the last one kind of commercially successful code was that was written. Maybe it was CFD++, or maybe it was this latest version of CFX. But I mean, do you think we'll see a new from the ground up CFD code, or do you think we're just going to patch on the old codes?
Brad, have a go.
Well, it's kind of hard to say. I imagine there will be. The thing is that these days, to get a CFD code to commercial capability, just takes a huge amount of effort. Mm-hmm. It's a huge effort to do that. So there are incumbent codes. CFX is one of them. Mm-hmm. For another code to get to that level, it's a huge job. So I don't know. If someone can afford it. But I would go back to what Paul was talking about, surprises. It seems that in the early days, in the 80s, when we were working on CFD, there seemed to be a lot of focus on development of methods. And I remember at the time I was working on multigrid, and I would read these papers by this guy named Aki Brandt, that he was doing nonlinear multigrid and claiming to get solutions in 6 work units. So it's like 6 iterations. Mm-hmm. And I thought that would be the future, but I mean, we're nowhere near that today. So I think there's a lot of work to be done on the methods. Paul mentioned grid generation, which is still ridiculously difficult compared to what it should be. Mm-hmm. The other thing is turbulence modeling. I mean, right. Particularly in Ansys, who has the best turbulence model, the best commercial mm-hmm. turbulence modeling that I know of, due to the efforts of Florian Mentor and his team. I mean, they've made big improvements, but many calculations are still done with just variants of the K epsilon model, which came out in the 70s. So there's a lot of work to be done in terms of turbulence models. Yeah. So I think to a large degree, a lot of the advances in CFD have depended on the acceleration in computing. Mm-hmm. And so, we have huge amounts of memory compared to what we used to have. The CPUs run much faster. And so a lot of the gains are, riding the hardware capabilities, but I think there's still a lot of work to be done in turbulence and grid generation, in the fundamental numerical methods. I mean, Paul and I worked on evaluating certain types of nonlinear numerical methods back in the early 80s, and we have never much came of that, and I don't know why. So I think there is to some degree stagnation. I mean, what hasn't stagnated is the widespread usage of CFD. Right. But there's still a lot of room for improvement, and I agree with Paul on the point of quality. Maybe that comes to education and training as well. There's a lot of CFD calculations done, but there'd be a lot more quality involved.
There's a lot of wasted clock pulses out there.
Yeah, that's for sure.
That is true.
Yeah. We used to spend a lot of our time walking people through, how to use the software and how do you tell it's converged, and what choices have you made, and there's a lot to be learned by users on that front. I mean, the more that could be incorporated into the software, the better. And to a big degree, we tried to do that in CFX. I mean, one of the biggest differences between CFX and all other codes was the coupled multigrid solver. Right. And with that solver, it got around, for many cases, a lot of the cases of lack of convergence that other methods would yield. So these advanced methods can be built into the software, and I think more needs to be done in that area today. And if that could be done, then the quality would continue to go up.
More better, faster.
I mean, Eric, back to your question about a safety code for the future. On the one hand, it's kind of a shame if there isn't some new code for the future. It's kind of hard to imagine that there isn't. You think of the auto industry or whatever other industry, they keep reinventing themselves, and you would think the same thing would happen with CFD too. But it is a gigantic job, and I think it really needs a driver. So, in the 80s, the driver was, let's make the very first code. The first commercial CFD code, and so there was lots of companies doing this. And then in the mid to late 90s, pretty well everybody rewrote their code, CFX included, and probably all the others, because of two reasons. It was driven by parallel processing,
right?
And you really had to write your code from the ground up with that in mind to make it work well. So parallel processing, and everybody went from block structured grids to unstructured meshes in the 90s. So we need that next driver. If the next driver is some massive parallel GPU that could really work, or some new numerical method that really drove you to rewrite your software because there's a real big benefit coming from it. But at this point, it's kind of elusive, and you really do need a big driver to put that big investment in it. It's a giant investment, as you know. It's decade or more of tens or maybe 50 people working on it for a long time.
Be hard to catch up. Be very hard to catch up. Yeah.
Yeah. There's got to be a real motivator, or maybe the higher order methods will be a real motivator. There's lots of higher order codes out there, and I think it's still on the bubble when those codes, really give computational benefit for the accuracy. Or maybe someone comes up with a whole new approach to turbulence that isn't RANS, it isn't LES, but it's some other thing yet to be discovered, and then that causes everybody to rewrite their codes, maybe. Don't know.
Yeah. And
adaptation might be the other one. I mean, it works great in 2D, but, for code to be truly adaptive, to refine the mesh where it makes sense, and to do so in such a way that it doesn't, take a 100,000 node mesh and make it into 10 billion nodes or something like that.
Maybe
a better transient method, because in the early days we mostly did steady state calculations.
Right.
Now it's much more transient. So something that could overcome those challenges. I think Paul's right. If something could drive it, a new technology developed and something to drive it, then it would be worth rewriting all the codes. But until then, it's probably, patch on to or improve what we already have.
Yeah, which is good. It's easier to do that. Anything else you want to add about the history of CFX or the future before I ask you the last couple questions here?
Well, it's still tremendous fun. It's still tremendous fun using the software. That's for sure. I mean, I'm using CFX every day, and it's tremendously satisfying, and it's really crazy the physics and the creativity of customers, end users, taking these softwares and using it in a way that a developer never even thought could be possible, but yet it's in the physics and it works. That's really cool.
Very, very cool. Yeah, very cool to see that. So that leads me really perfect to my next question for you guys. What are you guys up to these days? Paul, you're still doing consulting, I think, and I heard something about trees in your life, Brad.
Wow. Yeah, Paul's still slaving away. I worked hard and long.
Yes.
in the engineering, simulation, CFD, and miscellaneous business. So my days of doing that are over. So I'm retired.
Excellent. Very good.
So I've always liked to spend a lot of time outdoors, and I do a lot of that now. So I'll while I have a lot of fond memories of doing CFD and engineering, there's lots of younger guys that can, take up that challenge.
Good.
But you're up pretty late at night some of these days too in your new career.
Yeah, well, I always was a bit of a night hawk. I think coffee in graduate school did that to me.
Yeah, I was thinking of your band these days.
Oh yeah, well, I play a bit of music, but that's
fun.
Oh yeah, no, he's understating it.
Yes, I'm also trying to draw it out of him, but he's being modest. And I'll just leave it at that and say you can be a world-class numerical simulation expert and play a mean guitar at the same time. So is he Brian May? I don't know. Astrophysics and the Queen, yeah, but it's pretty good. You can be multifaceted, and it's one of the things we like about Brad is.
I'm of the same vintage, so we can leave it at that.
How about you, Paul? Why don't you tell us about what you're up to?
Yeah, so I'm doing CFD consulting. The company's called iSimQ. So I'm here in Canada and I have a sister company in Germany, iSimQ GmbH, and stands for Innovative Simulations with Quality. So we help customers by and large that are already using the software and mostly CFX, and we help them get more value out of it, either get into some new technology in the software that they haven't gone into, so maybe unsteady turbo machinery instead of steady, or something along those lines, and just help them get more reliable quality and use it in a creative way that maybe they haven't had a chance to figure out on their own yet. And so we're consulting all over the world and really having a great time. It's really satisfying working directly with the end user on the coal face, trying to make their machine better, And
that reminds me of a question I skipped that I'll go back to that just popped in my head is, so you're out there using the code now that you wrote portions of, both of you wrote portions of many, many years ago. Is there a decision you made back in the day, or maybe doing the rewrite that became the CFX code, that you wish you would have done something different?
Oh, we should have started unstructured in the 80s. That's what we should have done.
Yeah, there's when I use tools I wrote 10, 15 years ago, what was I thinking?
Yeah, I think we focused a lot on the technical, because Paul and I were fundamentally technical guys, but on the business side, getting things to market sooner is so important. And I think with CFX, and I should point out, I didn't write a line of CFX. I mean, what I did is I worked on numerical methods development. I worked on task flow, and then task flow morphed into CFX. So, maybe some of my lines made it into CFX, but they are undoubtedly rewritten. And there are guys like Dan Williams and Paul Gilbert that did, a ton of work on making CFX what it is. And, I didn't do much of that. I ended up working a lot with customers. Like Paul was just saying, it's rewarding to work with customers and to help them solve challenging problems. And I did a whole lot of that. I actually didn't write too many lines of CFX. But, to your question, we did some things in CFX that delayed getting to market. And they were allegedly at the time for technical reasons. But, in hindsight's 2020. I wish we hadn't done some of those things and got to market sooner, because when you get to market sooner, then you can generate more money. With more money, you can do more development. And I think that slowed us down a little bit. I think, a lot of the technical decisions were very good. There was some very strong technology. I think in one area or so, we took it a bit too far. It delayed us to getting to market. And I think we could have ultimately developed the product even faster and further by taking a slightly different approach. But that's hindsight. On the other hand, it's a great piece of software.
It works
today. It's in many companies and engineers use it worldwide every day. They can't survive without it. So there's great on the upside. But yeah, you can always look back and see where you could have done things better. And I think that's the main one that I see.
Yeah, that's a really good advice for people. And nowadays when we work with startups, we always talk about this idea of a minimum viable product. I don't think that was really a concept back then, right? And I think through learning the hard way, people have realized that you just got to get whatever you can get to market with as a good working product, but the minimum viable. It's still viable, but it's the minimum size, and get out there as soon as possible. It's good advice. Yeah.
I mean, I didn't get in front of customers very often in the early days because I was just pure technical. And if I went out there and started talking, it would just be total gibberish or scare them off thinking this was too complicated. We were all excited about our technology, so we'd love to talk about it. But the customer actually at that point, they were just like, well, can this solve my problem or not? And we're talking about, multi-grid and blah, blah, blah. And, it was a while before we came around to the real business aspects. And certainly Brad led the way on that, Brad and George. But myself, they kept me in the back closet there.
Well, I still remember, and I don't remember where it was, but you were on a panel. I was in the audience. You were on a panel, and a younger user, I may have been in development, or a user was started to argue with you about some aspect of the solver in CFX, and he had no idea that you had been involved in the early writing of that. And I wonder where that
was.
It was some event. I remember you up on it was probably one of the sales kickoffs.
Okay.
And one of the Ansys sales kickoffs, where, for those who don't know, every year everybody in the Ansys family gets together and kind of kicks off the year. And I remember just shaking my head and going, this kid has no idea how wrong he is. But you were very gracious about it. You didn't stand up and say, I wrote it, damn it.
That might have been the conference with the mullet wig, I think.
I think that it may have been. We would try and make them fun. So there may have been some costumes involved in some of these things. Speaking of young people, not to malign millennials and Gen Y folks too much, although I do enjoy doing it, is there any words of wisdom to new grads out there, or people that are still in college, that you want to pass along to them before we sign off?
Speaking for myself, I benefited from a very good classical education, and I think that's still important, learning the fundamentals and a lot of the stuff I learned as undergraduate and in grad school. Some of those ideas made their way into the software. But when it comes to using the software, you can't beat knowing the fundamentals, because when you do a calculation, you have to say, well, does this calculation make sense? And what yardstick do you use to make that judgment? Well, if you have a good understanding, a fundamental understanding of fluid mechanics and heat transfer and thermodynamics and whatnot, then it makes it a whole lot easier. So I think, I know that the undergraduate curriculum is really crowded these days, and people are all enamored by computers and the web and whatnot. But learning the fundamentals as an engineer is really, really important. And those that did and were good at it, well, we would see that in their calculations. Right. Those people would be successful, or more successful than others who really that paid a whole lot less attention in class.
So true. I agree with that one. How about you?
Well, simulation has been tremendously good to me, and it's still very satisfying and exciting, really, even for me, even doing some new calculation on some new device. And if someone, when you're graduating, if you can somehow be fortunate enough to latch onto something that really turns your crank, I know it's all cliched, but it really is. You're tremendously fortunate, and I hope some guys can be fortunate out there and get into CFD and get bitten by the bug, or simulation in general. It predicts the future. That's which is, I think, pretty darn cool. You can predict how your device is going to work before you get there. And I was lucky enough to stumble into something that still is very satisfying after 35 years or whatever. And I think that makes it so much easier. Whatever it is you're heading into after engineering, don't do it just for the money. I know that's all cliched, but find something you really love and go for it.
Yeah, that's really, really good advice. And I think all three of us are fortunate enough to have, on purpose or by accident, ended up doing that. And it has been, it's just a lot of fun. And it still is. It's changed a lot, but I still enjoy, digging into these problems and solving them. And like you said, predicting how things are going to behave is a lot of fun. It's a lot of fun.
It is.
Cool. Yeah. Cool. And fundamentals, I can't overstress that. I ask that question of everybody, whether they are a new grad or experienced folks like yourself, and almost everybody agrees with that statement. We really need to get back to fundamentals. There's a lot of models getting built out there that just don't make sense. And if you don't understand why does flow separate, then you're just throwing a turbulence model on a problem. If you need to understand the physics behind it so that you can pick the right one. So,
and I think to some extent you really need to understand how the CFD is approaching that physics.
Yeah.
You really you need some numerics.
Mm-hmm. Yep.
To make the judgment.
Yeah. Why does this not? It doesn't look right. Why? So I totally agree with that, and it's so true. And we try to reemphasize it when we get a chance to talk to universities, and I encourage others to. You really don't need another team building class. How about some basic numerics or some basic fluid dynamics, which tends to get thrown into the elective pile these days. So.
And what's more fun than that?
I know. I love that class. It's one of the few I remember to this day. That and thermodynamics were my two favorite in my senior year. So. Still use them today. Well, thanks, guys. I really, really appreciate it. You know that the invitation is open anytime you're out here in the Southwest. Let us know. We'd love to host you and see you guys again, and hopefully we'll meet up at future events.
All right. Thanks a lot, Eric.
Yeah, thanks, Eric. Thanks very much.
Enjoy. Thanks a lot.
Okay.
Bye-bye now.
It truly is fascinating to talk with the people that were deep in the weeds in the early days of these tools. We kind of forget that at some point there was a room full of young engineers slaving away at a keyboard to make these things that we use every day. It's really a well-structured tool with a lot of very deep capability if you've ever used CFX. And if you listen to how user-focused and technically savvy these two are, you can see why the tool is the way it is. This was the third interview with founders of tools of the Ansys suite. The first one was back when we talked to John Swanson, the founder of Ansys. And then actually the last episode we published, I didn't realize this until I was preparing this episode. Episode 44 was the last one, or two ago, actually. We spoke with David Saban, who was one of the founders of Granta. Granta is a tool that Ansys acquired recently for material intelligence. And along with explaining what Granta is and how we can use it, he did talk a little bit about their origin story. So we'll add that to the list of growing founder interviews. So we're working hard to line up our next one, and we'll let you know when we have it. Let's go ahead and take a commercial, and then we'll come back and finish up.
Hi there. Eric Miller here to talk in a little more detail about a topic we bring up a lot in these podcasts: customizing Ansys products to automate processes or add functionality. A significant portion of PADT's consulting work in the simulation world is working with customers to write custom software that sits on top of or even inside various Ansys products. These programs can connect a legacy solver, import proprietary boundary conditions, or implement a new material model or custom fluid behavior. But most of the time, we work to write vertical applications that automate and standardize a specific customer simulation process. From chip packaging to family of parts simulation to turbine wheel geometry optimization, we can work with your team to provide productivity improvements that can make things up to 10 times faster than the current process. To learn more, contact us at info@padtinc.com or call 480-813-4884 and ask about Ansys customization and automation. A little bit of programming can create an order of magnitude change in productivity.
So not a lot of news to report. I'll just talk about the stock because that's news. Today is Friday, September 6th, and the price this morning before the market opened was $218.09 a share. And yesterday it looks like it set an all-time record high of $219.59. So congratulations to the Ansys stock. Not bad considering the ups and downs that our market continues to see. if you can compare year to date, Ansys is up 58.45%, while the S&P 500 is up only 21.57%. So not bad at all compared to the rest of the market. Don't really have any Ansys news to share. I've got one bit of PADT news. You may have seen a press release we put out. We just installed our largest additive manufacturing system ever. It's an Stratasys F900, and it has a build area of 36 by 24 by 36. It's a fused deposition modeling, or FDM machine, and it does all the materials that Stratasys has to offer, including some really cool high temperature, chemical resistant, very strong polymers that we really love. We've been users of that technology since day one, since they introduced their machines back in the 90s, but we had never had the opportunity or need for the large machine, and we finally got to the point where our customers were asking us to make some parts for them on that size. So at 36, 24, 36, we can make some big parts. So do consider PADT for your 3D printing needs, especially if they're large. Publication-wise, Ansys blog, I'm only going to talk about one thing I saw on there. Again, it's Granta, which we were just talking about our interview with them. They wrote a really cool article called Paper, Plastic, or Jute. And they took a look at using their material intelligence tools to compare and contrast, kind of optimize different materials for a product, the cost, the economic impact, the long-term cost. It's really cool. You got to read the article. They did it about shopping bags, which I thought was kind of fun. I won't give you away the winner. You have to go read the article, but that's in the Ansys blog. Also of note, the latest issue of Ansys Advantage magazine is out, and their focus is on fluid dynamics, so appropriate for our interview. So do read that. There's some pretty cool articles. And as always, the fluid dynamics guys always have the best plots. There's some really good graphics in there. On our blog, we don't really have anything new in the Ansys world, but I do have something about simulation to share with you. And it's really a link to another website. So when I was at the Rapid TCT conference in Detroit this year, I was interviewed by the editor of the a magazine or a website called Additive Manufacturing Media. And we talked about simulation in additive manufacturing, so appropriate for this cloud. The first interview, I give 3 reasons why I think where and why we should be using simulation and additive. And you have to listen to the interview to find out what those 3 are. And then we went off on a little bit of a tangent about topological optimization and generative design. And it was enough of a tangent to make a separate interview. So there's 2 out there. Do go to www.padtinc.com/blog, and it should be near the top, or you can search for video interview to find the links. And it was really fun talking with Stephanie Hendrickson of Additive Manufacturing Media, and we hope to spread the word about the power of simulation in additive with them in the future. Upcoming events, our next webinar here at PADT is on the 11th, and it's on Fluids Innovations and Ansys 2019 R3. So that we'll follow up with a podcast actually after that one. The R3 isn't actually released yet, so we can't really talk about it until the day after, which is the 11th. Other PADT events, the first event we attended this month was here in Vail. So that was a lot of fun, as I said earlier, and I'm really enjoying it. It's going to be tough to go home. Next is a webinar we are doing with an organization called the Manufacturing Tech Council. I'll be on a panel discussing the advances in additive manufacturing. I'll get a plug in there for simulation, but it's really about our journey, PADT's journey as a company over 25 years, starting with our SLA 250 sterile lithography machine back in 1994 and up through the acquisition of our F900 just a few weeks ago. We will also have a booth, and I will be on another panel at the annual Experience IT Tech Conference in Albuquerque, New Mexico, and that's put on by our friends at the New Mexico Tech Council. We're members of the Tech Council, and we're very excited about the activities they have going on there. That's September 13th, so I'll be in town for that, and please do stop by if you are listening from Albuquerque and going to be at that event. We're also going to be at the 2019 Arizona STEM and Innovation Summit in Scottsdale on the 17th. If you're local, to Phoenix and are interested in STEM, maybe your kids are involved in STEM, please do find time to come to this event. It's really great and an opportunity for everybody in the science, technology, engineering, and math education ecosystem to get together, industry, educators, students, parents, and talk about how we can do a better job with STEM. And that's put on by the Arizona Technology Council. And we're going to finish up the month, a very busy month, with our big annual Colorado customer event. It's called the 2019 Colorado Additive Manufacturing Day, but we will be talking about simulation. In fact, some folks from the Ansys additive team will be flying in to speak at the event, and it's really for all of our customers. It starts a little bit after noon and goes till the early evening. It's outside there at a brewery by the river in downtown Littleton, Colorado. We highly recommend you stop by, even if you're not a big 3D printing person. We'll have a lot of folks from PADT there, both on the Ansys and Stratasys side. So please do register. All of these events, you can find links for more information and registration at padtinc.com/events. And that's it. Thank you. I'm going to edit all this together and then hit the road for a 2-hour beautiful drive through the Rocky Mountains. It's going to go ahead and spend the rest of the day at our Littleton office and then head home late tonight, grudgingly. If you've never been to this part of the country, I highly recommend a drive through the Rocky Mountains in the summer. It's just gorgeous. Don't forget to subscribe to www.padtinc.com/opt-in so you can get all of our news and events. Spread the word about our podcast. Please leave a comment. Please rate us on whatever tool you use to listen to podcasts. And don't hesitate to reach out at podcast@padtinc.com. Thank you for joining us for the All Things Ansys podcast, episode 46. As a reminder, this podcast is not affiliated in any way with Ansys Inc., and the opinions expressed are those of the people on the show only and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.